Oh, wrong one. Uh-oh, now we're in trouble. I got to do this first. Well, why isn't it letting me out of here? Now it'll let me out of here. Okay. Oh, I see why I don't have it. It quit. Oh, well. Okay. What I was going to show you was the list, current known list of mitochondrial disease. And in the list that scientists are actively working on, that are also, now look at this list. These are diseases of the mitochondria. Alzheimer's, dementia, chorea, diabetes mellitus, deafness. You just look at the list. Epilepsy, gastrointestinal reflux disease. I mean, it's just, name something. Non-insulin dependent as well as insulin dependent. Sudden infant death syndrome. This is just a partial list. If you get over here and look on the researchers list, it's literally every disease you can imagine is a disease of the mitochondria. Oops. All right. Is this the good one, Phil? Well, I actually like the one that's, oh, here it is. I want the one that shows, no, that's not it. Anyway, to answer your question, Lipitor doesn't help the mitochondria. Does nothing for the mitochondria. As a matter of fact, it impairs your ability to improve your position on the Anacat map. It is a catabolic molecule. It impairs the body's synthesis of squalene. Squalene is what the body uses to produce ubiquinone. Ubiquinone, otherwise known as CoQ10. Well, does that mean I don't write prescriptions for Lipitor? It does not mean that. I write prescriptions for Lipitor. But the point is, if you can reverse the disease that drug was designed to treat in another way, that's my preference. I'm kind of a drugs last rather than first guy. I'm not an anti-drug. I'm not a chiropractor, okay? I think maybe it's this one. No, shoot. Well, I wanted the one that shows the wall of the cell, the mitochondria in the wall, in the cell, and then the electron chain transport on the mitochondria. Is it? Might be the very... No, I don't think it's that one, but we'll look and see. Well, this isn't bad. Any biochemists in the office, in the audience? There usually is. Well, this little guy is the mitochondria. And what we've learned, and I don't mean we, what science has learned, is how many you have and how well they work is how healthy you are. It's that simple. And you can change how many you have and how well they work. And they're little tiny guys that you inherit wholly from your mother, by the way. The genetics of mitochondria come entirely from your mother. But the effective, unlike all the rest of your genetics, they come from both. But the ability of this mitochondria to function, which within a certain biological range is defined by your maternal inheritance, where you are in that range determines how healthy you are, and that's a function of other things in the cell, the cytoplasm, that are a mixture of both of your genetic components. So it's not just, gee, Mom lived forever, so I will too. Believe me, it's not. I wish it were that simple. But, so here's this little guy. I don't know what that looks like, an articulated peanut to me. He's inside the cell. These are some gorgeous things. Basically, this is called the citric acid or Krebs cycle. All this fancy chemistry, if you want to watch it, is basically what happens to a glucose molecule. Now, actually, the glycolytic phase isn't in this phase, but this is going to generate what's energy to the biological system called adenosine triphosphate. ATP is what we want to have. And there's, by the way, see this thing called coenzyme A? Well, we'll get into that. But you can see a lot of these little all these things going on. And here's why what you do makes all the difference in how this functions. Now, I want you to notice how many, and these are little atoms, see? Every time you see one of those little atoms moves, it didn't do it by magic. And here's where the genetics come in. Each one of these little movements, aren't they, you know, neat. Oops, we made a water molecule. Imagine that. And you've heard of citric acid. Water, cis-iconic acid. Now, the reason why you care about all those little movements of all those little molecules, you say, my God, give me a break. Let me tell you why you care. And here's where, if you improve your place on the ANACAP map, you have changed your genetic destiny. Every single one of those movements didn't happen by magic. It happened by catalysis. A little tiny piece of protein, a little chain of amino acids made that chemical reaction happen at that rate. Now, all the chemical reactions in the body happen naturally, but they happen so slowly that in the absence of catalysis, well, none of us would be here. Let's just leave it at that. There would have been no evolutionary biological history. So these little molecules make these chemical reactions happen at a rate that allows life to go on. And those little molecules that make these chemical actions happen come from, guess, your genetics. You have genes that code for, write for, create each of those little proteins that makes each one of those chemical reactions happen. Millions of reactions, and they're all governed by an actual little guy in there pushing those molecules around. A little guy pushing each one of those molecules around every single time. Carbon dioxide, heard of that? You know where that comes out? The exhaust pipe, right? One of them. Well, each glucose molecule makes about 30 molecules of adenosine triphosphate, ATP. But notice how many amazing chemical reactions are going on here. And we're just getting started. Every one of these movements is made by a nanoscale machine moving these molecules around. And every one of those little nanoscale machines is made by your genetics. And here's the cool part. You can make your genetics healthier through we now know about reverse transcriptase. We now know that you can take demand side. And by the way, let me give you a practical application. Notice I told us with theory you could actually make a difference in practice. If you go out and jog, you don't do any of this. You don't fix this. Let me show you why.